Okay, hi guys. Thank you very much for all those people who filled in the questionnaire. It's about a third of the class, give or take, about 12, 13 people, so not entirely representative. But if you have given me your feedback, thank you very much. If you haven't, it's not too late. Do give me a shout if there's anything that we don't go through. But I just really want to have a look at what you told me that you thought you did well at and what you didn't do so well at. I thought I'd give you a little bit of help, a little bit of support, and I've got a sort of a little bit of a revision sheet that you can sort of have just to have a look at the areas perhaps you struggle with a little bit. So, whizzing through it first, pure and formulation. We did that right at the very start. I'm surprised by the number of people who aren't very confident with that. Pure means contains one type of atom, one type of molecule only, where a formulation is a mixture with a purpose. So if you get a fizzy drink, that'll be a formulation. It'll be a mixture of water and sugar and carbonation and flavours and all sorts of things. Whereas if you get pure water, that would just have H2O molecules in. So that's a definition you've got to learn, guys. If you're not sure, you need to go back to your revision guides on that one. Right, I can describe how to perform chromatography and perform RF values. So most of us were pretty good with that, which is excellent, so well done. So bit of paper, draw a pencil line along the bottom, put the dots on the bottom, put it in the solvent, it moves its way up. And then that separates the mixture, and you can use it for analysis as well, because when you get to the end, you take it out, you mark off the top where the solvents reach with a pencil line and measure the distance between the first line and the second. That's called the solvent front, and then you measure how far the dot has moved from the start and divide that number by the solvent front. That gives the RF value. And you've got a worksheet with that on it somewhere, so do have a look through that if you're not sure. Right, melting point stuff. Again, I was surprised how many people were struggling with this one. Melting point for a pure substance is a set number, 120 degrees, for example. And it won't be a range, it'll be a pure number. If something is impure, it won't be that definite number. If it's higher than that number, it's definitely impure. If it's lower than that number, it's impure as well. The closer you get to the purity, as long as it's below, the purer it is. And if it's a range, it's impure. So if you measure the purity and you get 116 to 118, it's not pure because it's a range. So the closer to the definite value is the purity. Okay. Right, tests, hydrogen, oxygen, chlorine, carbon dioxide, that's separated us quite a little bit. So hydrogen's a squeak pop test, oxygen relights a lit splint, chlorine bleaches damp blue litmus paper, and carbon dioxide turns lime water milky. So if you don't know that, it's worth revising that. Right, flame tests. Generally pretty good on flame tests, so well done on that. I think most of us are fairly confident. Again, I assume the people who weren't, it's learning all of the colours. Right, flame emission spectroscopy. Now this is the one people struggled with. And interestingly, I've done this with you two, and they struggled with this as well. I've put information on this on the handout sheet at the end, so do print it off and have a look. But very simply, how does it work? It's a POSH flame test. You set the sample on fire, you look at the flame colour, but the flame colour then goes through a prism where it's separated into a spectrum. Why it separates into a spectrum is because of the electrons in the shells of the atoms jump into higher energy levels, and then they give out energy. They give out specific bands of energy. That gives us a spectral line. We get a spectrum that's a fingerprint. There's different lines at different wavelengths of light, and they correspond to one type of atom only. So do have a look on the worksheet if you're not sure. It's just a POSH flame test. Okay, precipitation test for hydroxides. Don't think we're so confident on this. This was one of the last things we did in school before we disappeared. So we did try and do it all practically. There is a video link on the sheet, so you can have a look at that and have a look at some of the ions tests. But the test for a hydroxide, for a metal ion, is you add sodium hydroxide. Sodium hydroxide is a colourless solution. You add it to the ions solution, and what happens is you form an insoluble precipitate of the metal hydroxide. So the metal bonds with the hydroxide, they bond together, and the colour of that precipitate, the powder that forms immediately, gives you some indication. So if it's green, it's iron 2. If it's orange, it's iron 3. If it's a bluish colour, it's copper 2 ions. If it's white, it could be aluminium, it could be magnesium, it could be calcium. Calcium we can identify with a flame test, and aluminium and magnesium is based on whether or not it redissolves. If it's aluminium, it will redissolve if you keep adding hydroxide. If it's which one did I say it was? Calcium, sorry, it won't. Sorry, magnesium, it won't. Right, carbonates, dead easy. If it's carbonate ions, you add an acid to it, it will fizz, as carbon dioxide is given off. We will come back to this in Module 7 when we look at the reactions of carbonates. So you will get an opportunity to revisit this then. Precipitate test for hydroxides. Again, this is another one we did practically right at the end. So what do? You have, if you think you've got a halide, that's a chloride, a bromide, or an iodide ion in solution. You add to it acidified silver nitrate. So you need nitric acid and silver nitrate solution. You add those two, and what happens is you form the silver halide ion at the end. And silver halide is a precipitate. So if it's chloride, it's white. If it's bromide, it's cream. If it's iodide, it's yellow. You do need to learn that on the equations. So do go back through your notes and learn them, guys. Test for sulfate ions. Again, not 100% confident with that. Very similar. You add to it barium ions, normally barium chloride, so hydrochloric acid plus barium chloride. When the barium reacts with the sulfate ions, then it forms an insoluble white precipitate of barium sulfate. So that's the test for sulfate ions. Chuck in barium chloride and hydrochloric acid, white precipitate. Right, potable water. Now I was surprised by how few of you remember this. Potable means drinking water. So how do you make water drinkable? Well, there's 3 stages. You find some sort of water reservoir, whether that's a reservoir, a lake, a river, falls out of the sky basically. Then what do? We have the first stage, which is sedimentation, where you remove big bits of solid. The second stage is filtration, where you remove little bits of solid. The third stage is usually chlorination, but it's sterilisation. It kills off any microbes, any bacteria or viruses in it. You can use UV light, you can use ozone. We tend to use chlorine. You can boil it if you've got money to burn, but we don't do that. Right, desalination by 2 methods. This is a bit one we're not 100% sure on. I put this on the worksheet so you can have the information sheet so you can have a look. 2 methods. Method number 1 is distillation. You boil the water, you condense it down a condensing tube called a Leipzig condenser, and then what comes out at the end is water that's pure. So you've got your salty water at the start, you boil it so the water vaporizes, it goes up the tube, it then condenses, it goes into a colder tube, and it comes out as pure water. So that's method 1. Method 2 is something called reverse osmosis. It's effectively filtering it. You push salt water through a very fine filter under high pressure, and that will take out any salt from it. It's filtering out the salt effectively, and that's on there as well. Both methods are only done by countries that are very, very rich and have very little water. So you're thinking oil-rich nations, desert nations where they've got sea coast and they don't have a lot of rainwater. We don't do it because it's expensive. We don't need to. Right. How wastewater is treated. Again, you've done a flow chart on that. So it's the effluent going in, there's screening processes, there's anaerobic breakdown, there's aerobic breakdown, so decomposition, and then you get sludge coming off, which we then use for other things, and then we get pure water out, which goes back into the ecosystem. Have a look back through your notes, because there's a video on that, which is really good. Right, finite and renewable resources and examples. I was surprised by how many people weren't very confident on this. I would encourage you to go back through your lesson notes for that. So finite means it's running out. Renewable means that we can replace them as we use them. Okay, an example would be finite, it would be renewable, whereas petrol is finite. Like bioleaching and phytomining, I put this information on the sheet. Very, very simply, bioleaching involves growing plants and absorbing copper ions or very low concentration of ions in the roots. Phytomining involves, other way around. Phytomining is the one that involves plants, and then you burn the ash, and you extract it from the ash via electrolysis. Bioleaching involves the use of bacteria. So that's on the sheet for you to have a look at. It is one area people struggle with, but you did do a lesson on that, so do have a look through it. Right, life cycle assessment, you're all over that, and I'm not surprised because you did really well on the questions. How glass and metal recycled, generally speaking, we're pretty good at that. Again, look back to your notes if you're not sure. Alloys and the elements they contain, that's learning, guys. You need to know brass, bronze, amalgam, steel, and I would put solder on that. So there's 5 there, arguably, but make sure you learn them. They're on the sheet from the other day. Corrosion, generally speaking, pretty good. 3 things: you need iron, and you need water, and you need oxygen. If that corrosion is rust, for most of the metals, it's just the oxidation of the metal. Right, thermo-softening, thermo-setting. Some people are really good on this. A little bit, but people are not so sure. Look back through the video I did on this one, guys. It's to do with cross-links. It has very weak intermolecular forces between the different polymer chains. Then it's thermo-softening. If they form strong cross-links or covalent bonds, then it's thermo-setting. Look at the video if you're not sure. Composite materials. A number of people who don't know this surprised me. Again, it's the same lessons as the polymers one. Go back through it. Think about Bob and his lorry load of kittens going over the bridge with the crocodile. Okay, there's a good example of a composite material, reinforced concrete. Okay, what's glass made from? A bit of a mixed bag there. I'll put that on the sheet as well. It's mainly silicon dioxide, it's mainly sand. And it's silicon dioxide mixed with other things. The complicating one is borosilicate, which is high temperature glass, where you put boron in with it. Right, Haber process, you should be all over, and lo and behold you are. So, word and symbol equation, 450 Celsius, 200 atmospheres, iron catalyst, you should know. Le Chatelier's principle, I'll make the cat rider. If you don't know this now, we haven't got time to go through it in this thing, but please, please, please go back through your notes. This keeps rearing its ugly head. It's the second time we've met it. Okay, but you need to know how pressure, temperature, and concentration affect the Le Chatelier's principle. But very simply, if you change the concentration of something, you shift the position of equilibrium to reduce it. If you change the pressure, you shift it to the side of fewest moles of gas. Change the temperature, you'll shift it in the endothermic direction. So make sure you go back and learn that, guys, because it's going to keep coming back. We will look at it in the future if we get a chance, but just bear in mind this is a biggie. Get your head around it. NPK in fertilisers. I was amazed by the number of people who weren't confident with this. NPK, they're on the periodic table. N, nitrogen. P, phosphorus. K, potassium. All fertilisers contain those 3 essential minerals. Some contain magnesium as well. But learn NPK. If you don't know, break out the periodic table in the exam. Okay. How we make them from acids and bases. Apologies for the spelling mistake. If you don't know, I'm not bothered. I'm not going to go through it today because we're going to do it again in Module 7. We haven't done acids and bases. Fertilisers are salts. So we're just going to look at how we make salts from acids and bases later. This will become much clearer then. Okay, so that's everything really. That's the whole of the module, and you told me how you think you're doing with it. I'll ping out the worksheet which just has information on, so have a look through. Do look through the video. If there's any areas you don't get, all of the lessons that we've done online are still online. You can find them on YouTube, you can find them going back to Insight, but do watch them again. Because again, pausing and rewatching them will make it stick, hopefully. If you have any questions, comments, queries or concerns, give us a shout. Otherwise, guys, I hope you're all well, and I'll see you soon.